The frequency of the autosomal dominant condition neurofibromatosis is 1 in 3,000. What is the frequency of the allele for neurofibromatosis? Okay, so we start off with the Heidi-Weinberg equilibrium equation. We have p squared plus 2pq plus q squared equals 1. And for the dominant portion of that, we have p squared plus 2pq equals 1 in 3,000. So we set up this equation. The first thing that we have to know that wasn't mentioned in the notes is that for q is going to be a number that is very, very close to 1. So we assume that q is approximately 1. And we also assume that p squared is negligibly small. Therefore, when we do that, if p squared is negligibly small, that drops out of the equation of p squared plus 2pq equals 1 in 3,000. So we're just left with 2pq equals 1 in 3,000. So next, since we assumed that q was approximately 1, we're just left with the equation 2p times 1 equals 1 over 3,000. Next, to solve for p, we're going to divide both sides by 2. So 2p divided by 2 is p, and 1 in 3,000 divided by 2 is 1 in 6,000. So the answer for part A is 1 in 6,000. That's how we got it. For part B, it says, what is the frequency of the individual who is homozygous for the neurofibromatosis allele? So, if somebody is homozygous for that allele, that means that it's p squared. So we're looking for p squared. So p times p is 1 over 6,000 times 1 over 6,000. So that's our final answer, and that's how we get that. Okay, so for number 2, it says the frequency of homocystinuria, an autosomal recessive disorder, is 1 in 160,000. What is the carrier frequency? So the first thing that we do is that we set 1 divided by 160,000, we set that equal to q squared. Next, we solve for q. So to solve for q, we're going to take the square root of both sides. We get q equals 1 over 400. So we know that q is equal to 1 over 400. The question is asking us for the carrier frequency, and we know that that's represented by 2pq. So we know what q is, but we don't know exactly what p is. P in this case would be 399 divided by 400. But since 399 divided by 400 is so close to 1, we're going to round up and assume that p is approximately 1. So in the next equation, we get 2pq equals 2 times 1, which is what we assumed p to be. So 2 times 1 times 1 over 400, we get 1 over 200, and that's it. The carrier frequency of a sex-linked recessive disorder is 1 in 5,000. What is the frequency of the disease in males, and what is the frequency of the disease in females? So first of all, they tell us that the carrier frequency is 1 in 5,000, so we set 2 times p times q equal to 1 over 5,000. Next, we're going to assume that p, which is the frequency of the dominant gene or the dominant allele, we're going to assume that that's approximately 1 or very, very close to 1. And we're going to assume that q is very small. So we assume that p is approximately 1. Next, we substitute 1 for p. So we get 2 times 1 times q equals 1 over 5,000. The rest is algebra. We solve for q. Divide everything by 2, divide both sides by 2. So we get 2q equals 1 over 5,000. Then we get q equals 1 over 10,000. So the frequency of the disease in males is 1 out of every 10,000. Next question, what is the frequency of the disease in females? So, to determine the frequency of the disease in females, we know that it's a sex-linked recessive disorder, which means that females have to have 2 copies of an X gene with this mutation or with this disease allele. Therefore, the frequency of getting a recessive allele is 1 in 10,000. So we have to multiply 1 in 10,000 times 1 in 10,000. So we essentially have Q squared, which is 1 out of 10,000 squared. And that's it. Calculate F for granddaughter-grandfather mating. The grandfather's allele is passed on through 3 generations to make the fetus of a granddaughter and grandfather. Therefore, we have F equals 1/2 raised to the 3rd power, which equals 1/8. A couple has a child with cystic fibrosis. The father unexpectedly dies and the mother remarries. The frequency of cystic fibrosis is 1 in 2,500. What is the probability that she will remarry a cystic fibrosis carrier? So first of all, we should know that cystic fibrosis is autosomal recessive, which means that a person has to have 2 recessive genes in order to have cystic fibrosis. So taking that in mind, it means that we are looking at the Q squared part of the Heidi-Weinberg equation. So in this case, Q squared equals 1 over 2,500. Next, we're using algebra. We're going to take the square root of Q squared, and we get Q equals 1 out of 50. So if Q equals 1 out of 50 and P plus Q is equal to 1, we know that P has to equal 49 over 50. But there's an assumption that's being made here. The assumption is that since 49 over 50 is so close to 1, we're going to round P to equal 1. So that's our assumption. So since we're asking about the probability of finding a carrier, we're going to look at 2 times P times Q. So 2PQ is equal to 2 times 1 over 50. And again, we're assuming that P is equal to 1 or approximately 1. So 2 times 1 over 50 is 1 out of 25. So that's our answer. Next it says, what is the probability that a child by her new husband will have cystic fibrosis? The mother is a carrier, and we know this because her child has cystic fibrosis while she is unaffected. So for this particular problem, there's another assumption that's being made, and that assumption is that the new husband is a carrier. So carriers have a 50% chance of passing on a defective gene. So our equation is carrier 1, which is the mother, is 1/2, times carrier 2, which is the new husband, that's 1/2, times the frequency of carriers in the population, which is 1 out of 25, and that equals 1 over 100. So in other words, the probability of having a child with an autosomal recessive disorder is 25%, and we multiply this by the frequency of carriers in the population, which is 4%. What is the frequency of each of the 3 genotypes in the MN system if the frequency of the M allele is 0.8 in this population? So 2 alleles, we have M and N. We know that M is 0.8. Therefore, to find N, all we do is subtract M from 1. So 1 minus 0.8 equals 0.2, and that's how we get N. So now, to find the next part, we do M squared. So 0.8 times 0.8 equals 0.64, so there's 64%. Then we do 2 times M times N, which is 2 times 0.8 times 0.2, and we get 0.32, which is 32%. And finally, we do N squared. 0.2 times 0.2 equals 0.04, which is 4%. 64 plus 32 plus 4 equals 100%. What is the carrier frequency of cystic fibrosis in Ashkenazi Jews if the frequency of cystic fibrosis in Ashkenazi Jews is 1 in 40,000? So again, cystic fibrosis is an autosomal recessive disorder, which means that you need 2 copies of the recessive gene in order to activate cystic fibrosis. Therefore, we're looking at Q squared. We're looking at that part of the Heidi-Weinberg equation. So Q squared equals 1 in 40,000. The rest becomes algebra. So we take the square root of Q squared and we take the square root of 1 over 40,000 and we get Q equals 1 over 200. So we have Q. For this problem that we've been doing for the others, we know that P plus Q equals 1. Therefore, if Q is 1 over 200, then that means that P has to be 199 over 200. And since 199 over 200 is so close to 1, we just assume that P equals 1. So for the next equation, to find the carrier frequency, we just do 2 times P times Q. That equals 2 times approximately 1 times 1 over 200. That equals 1 over 100, and that's it. The gene frequency of the allele that causes Huntington's disease is 1 in 20,000. What is the frequency of Huntington's disease in this population? So Huntington's disease is an autosomal dominant disorder. So the key to getting this problem correct is knowing that the gene frequency of the allele is 1 in 20,000. So this dominant allele, P, equals 1 in 20,000. So that's the first step. Next, we're looking at the dominant portions of the Hardy-Weinberg equation. So we're looking at P squared, and we're also looking at 2P cubed, because if somebody is heterozygous for this, the dominant portion or the dominant allele will cause them to have the dominant phenotype. So we're looking at P squared plus 2P cubed. Since P is equal to 1 over 20,000, that means that if we multiply P times P, the number is going to be negligibly small. So that's an assumption that we're going to make for this problem. P squared is negligibly small. And again, the reason we're doing that is because 1 over 20,000 times 1 over 20,000 is a very small number. The other assumption that we're going to make is if P is a very, very small number, that means that Q is a number that's very, very close to 1. So again, we're going to make the assumption that Q is approximately 1. Finally, we substitute everything into the equation for the carrier population. We get 2PQ equals 2 times 1 over 20 times approximately 1 for Q, and that equals 1 over 10,000. So what we're doing is we have P squared plus 2PQ. That's the equation that we're looking at. And again, since we're saying that P squared is negligibly small, we're basically assuming that P squared is 0, or very, very close to 0. So that falls out of the final equation. And so we substitute 1 over 20,000 for P, and we substitute approximately 1 for Q. So that just becomes 2 over 20,000, and that becomes 1 over 10,000, and that's it. The carrier frequency of Menkes kinky hair disease is 1 out of 15,000. What is the frequency of Menkes kinky hair disease in the general population? So Menkes kinky hair disease is an X-linked recessive disease. So we're looking at the carrier frequency, and for the carrier frequency, we're looking at 2PQ. We're looking at that part of the Hardy-Weinberg equation. So 2PQ is equal to 1 over 15,000. Next, since it's an X-linked recessive disease, we're going to assume that the dominant allele is very high in the population in proportion to the recessive. So P is approximately 1. That's an assumption that we're making. We're going to assume that P is approximately 1 or very, very close to it. So if P is approximately 1, that basically falls out of the previous equation. So we get 2Q equals 1 over 15,000. Next, we divide both sides by 2. And we get Q equals 1 divided by 30,000. So since the disease is X-linked and recessive, the general population will largely consist of males who present this disease, since they have a single X chromosome. and the females will be a much smaller subset of the disease population, since they can have a dominant allele that will not cause them to present this phenotype. I would like to say thank you to Brianna Burlock and Nathan Steele for helping me understand this problem.